The session is live streamed already on Facebook, just to let you know.
Okay.
Okay.
Welcome, Dr. Ravi.
Good luck.
I'm very pleased to see you again.
Yeah, same here.
I'm very pleased.
Same.
Yeah.
Bye-bye.
Bye.
So I think we'll wait a few more minutes before we start so that the other attendees might be able to join us.
Okay.
Okay, until more attendees join us, I'm going to start with some remarks and introducing Dr. Karnib. First, I'm going to start recording the session. Okay. So, hello everyone. Thank you for joining us today in this exciting webinar. We are very pleased to have with us our guest speaker, Dr. Ali Karnib, Professor of Engineering at the Lebanese University, who will be presenting today on modeling the water energy food nexus, bridging science and policy making. Just a few remarks before we begin. The webinar is expected to last for 1 hour. The session is recorded and live streamed on Facebook for those of you who prefer to access social media platforms. All attendees and parties are muted with their video off. If you have any questions, please feel free to address those in the chat box here on WebEx or on Facebook as comments, and we shall respond to those in the Q&A session. Just a quick introduction of Dr. Karnib before we begin. Dr. Karnib is Professor of Engineering at the Lebanese University. He holds a PhD in Civil Engineering from Artois University in France. He's been working extensively on a wide range of issues in relation to sustainable development, namely sustainable water resources management, water energy food nexus, and assessment of climate change impacts on water resources. Professor Karnib combines strong academic credentials with extensive experience in project management and international consultancy services, both at policy and field levels. He's a member of the editorial board of the International Water Utility Journal and member of the International Scientific Committee of the Water World Congress of the European Water Resource Association. Today, Dr. Karnib will present a quantitative WEF nexus assessment methodology, or what he refers to as the Q-nexus model, and will explain to us how this approach is used to analyze WEF policy scenarios for improved long-term outcomes. Without any further delays, the floor is yours, Dr. Karnib, if you wish to start your presentation.
Thank you, Sibel, for this introduction. And also, good evening, everybody. Thank you for your participation and for your interest to this lecture. I would like first also to thank Prof. Rabi Mukhtar, Dean of the Faculty of Agricultural and Food Sciences at AUB, for this interesting webinar series. The title of my talk is Modeling the Water Energy Food Nexus. So I will start sharing my PowerPoints. Okay, so hope you are seeing my screen now. You that split my presentation in two parts. The second part will be presenting the Q-nexus model web tool. So I will enter directly into the web and to show you how to use this web tool to make simulation and to make analysis of the water, energy, and food nexus. Let's start to give some words first, because our session is mainly on the modeling, so we will not will be a little bit fast in introducing the nexus to have the time to introduce the modeling system. So firstly, just let's start with give some words about the nexus approach. So as you know, that the advantage of the Nexus approach is that it can recognize the interactions and impact from one sector to another. So this is mainly the important feature or advantage of the Nexus approach. So this means that every sector, it have impacts on the other sector, and vice versa, the other sector will have impacts on the original sector. And this could be applied for the water, energy, and food, as we have the three sectors. Then the interaction will be between these three sectors. Now I have a small question for the participants. Suppose that you want to differentiate between this Nexus approach, this Nexus concept, and the IWRM. How do you figure out the difference? The IWRM, this is the Integrated Water Resources Management. So it's an integrated, and the Nexus approach is obviously also an integrated system. So how you imagine the difference between these two approaches? I will not answer directly the question. This question, I will let you think about this, but let me give you to answer this question. Actually, the answer is based on the interaction itself. When you are working on the IWRM, are you taking into account all the interactions from all the sectors that are integrated in your system? So if yes, okay, so how? If yes, did you take into account impacts and the indirect impacts? You have to ask yourself. Ask you a question, you can think. You will see the modeling on the Nexus, and you can, if you keep with us until the end of this presentation, you will be able to answer these two questions very easily. Now, let me give you, before starting modeling, just a chronological evaluation of the Nexus concept. Of course, the Nexus, it's not new, it's an old concept. But what's new is that we have now some main focus events that give this Nexus an importance. And if I want to give you these, let's say, focus events, recently we have in 2011, the Bonn conference that give us very push into thinking and starting. If I ask you, for example, as a global estimates, or even if you think about your country, okay, to give me, for example, what are the water quantities withdrawal for energy production? Or what are the water quantities consumed for energy production? So in here, you could find that the first question was withdrawing, and the second consuming. Difference between these two. What are the energy quantities used for water in your country or globally? What are the water quantities used in food production, also in your country or globally? What are the energy quantities used in food production? So all these questions, do you have the answer, the quantities used in the answer of these questions? Think about it. Okay, now let me give you just a rapid overview. For the first question, we know that the global estimates of water used in energy production is 2% as consumption, but as withdrawal, we have 15%. For the global estimate of energy, the energy used in water represents around 6% of the total energy used. This is a global estimate. Of course, these vary widely when you go to national systems, because in the national are different. There's vast differentiation between global and national evaluation. Of course, in the agriculture sector, we have as a global estimate 70%. And also the energy in agriculture is in food. There's an amount. There's a global estimates. So we have all these estimates existed, and we can think now how to compute these estimates nationally for your countries, how to get these values in your country. Now, why we need models, actually? The question that we have to ask ourselves, why we have to put efforts to produce models? The main reason to make models or to produce models or to develop models is to because models can produce information for policy making. So the final use of models is policy making. We have to inform policy making or policymakers to choose the best alternative among many alternatives that we can use in policy settings, in the future policy settings. So models are important for policy making. How we can use models in policy making? Actually, we have, as usual, we have many scenarios, and we have to choose one of these scenarios to be implemented. And models can inform us the effects, the impacts of each of these scenarios to find the best one that have a very future good impacts in our systems, in our all systems, not only one sector, all the sectors. Because we are talking about scenarios, so if we back to the water, energy, and food, how we can imagine or develop a scenario? The scenario could be implemented. What are the variation? What we should variate in scenario to develop this scenario? First of all, we might, for example, change the end use of any set of any quantity of any sector that we are using. For example, we need to increase water demand. So this is one of the variables of a scenario. Another variable, we might, for example, change the technology option that we are using to produce this, let's say, this resource. I give you an example. If I'm for example, using groundwater and surface water, and some countries may use desalination. So I have different options to use or to produce water. So now, if I change this technology, what this might have impacts on our and on the sectors. Also, the allocation. I might change allocation in a scenario. For example, back to the water example. If I'm using for agriculture sector 60% surface water and 40% groundwater, if I change these percentages, how this might change the whole system, the three sectors together, because these three sectors are interconnected. Any change that I made on one sector, it will reflect, it will have impacts on all other sectors. So this is example of the scenarios. Now, a very important concept that we should know, and I cannot proceed before that I explain this concept to you about the nexus, because the nexus is very important to understand the direct and indirect effects. To let you understand that, I will give an example. Imagine that you are a policymaker in a country, and then you choose or you decide, you make an estimation and you decide that you need additional food in your country. So you make the order, or you said that, okay, we have to produce additional food. So now, in your opinion, when I have to produce additional food, I need additional water to produce this quantity of additional food. And of course, I need additional energy to produce this additional food. This is what we call the direct values or the direct effects of my additional food that I demanded. Now, the question, do you think that this is all the additional quantities that I needed for this additional food in terms of water and energy? I know you might answer, some of you might answer, yes, this is all the quantities that we need for water to produce food, and this is the total energy that we need to produce this additional food. But, and maybe some of you answer, no, we need other quantities. So actually, for the first type of answers, if they said this is the total values of water and energy for this food, this is wrong. And I will explain to you why this is wrong. Because actually, this is the direct effects, but we have to look into the indirect effects. What are the indirect effects? This additional water that I needed for the food, it needs additional energy. And it might need also additional water. And also, this additional energy needed for food, it might need additional energy, and of course, it needs additional water. And so on. For the additional needs additional, and so on. So actually, you will look that this could be infinite additional quantities that go through, and all these quantities is the indirect effects of my decision to make additional food. So you see that the problem is not very simple, it's a complex problem. And as you can see, and back to the IWRM, the IWRM models are taking only the direct effects into consideration. That's why in the Nexus systems, we have to go more through the indirect effects. And actually, if I want to answer the question, what are the additional quantity needed for this additional food? I have to make the summation of all these quantities that represents the direct and indirect values to give the total water input. Now you can see the difference. It's very important to know that in real systems, the indirect effects are present and present very surely, okay? So we need that, we need also to compute these indirect effects in a system, in a model. Now, if I want to build, let's say a TOR for a model, for a quantitative model, I need this model to respond to policy scenario. I need to consider the demand and technology variation. I need this model to estimate the direct and indirect impact. So all these features are needed in this model. And also it should inform policymakers and so on. Fine, now with this introduction, I can to show you how to build a model. And of course, I will use the theory. This theory could also be applied if you want to change or make any variation in the model and so on. But you can appreciate the modeling from the theory that developed for the Q-Nexus model. The first thing that, since we are talking about quantity, any quantitative model needs a balanced equation to be built. So we have to start from a balanced equation. This is very important. The first thing that we have to set the balanced equation. In our model, in the QMax model, we set a balanced equation. This balanced equation actually is very simple. We said that we have a certain amount of quantities that are produced at the supply side. We call this amounts as intersectoral use, okay? This is the supply side. Plus the quantity used at the demand side. This is what we called in the model the end use quantities. If I make this summation, I could have the total use of any resource. So now this is the balanced equation that I'm using. Now I want to develop more this balanced equation. This is a very simple balanced equation. Now, if I want to develop more, so this is my balanced equation. The first intersectoral use, it's represented by this matrix. And in this matrix, you can see, I will use my pen. In this matrix, you can see that the sectors are set in columns and in rows in front of each other. Okay? So this is the matrix of intersectoral use. And here we have the demand side, the end use. It's a vector. Okay? And the total use will be a vector. Of course, we have to make this is not a summation of matrices, it's a summation of rows of matrices. Don't confuse with the matrix calculation. Now, where is the balance in my equation? Okay, the simple equation that I showed you. The balance is here because any value here, if I put any value, this value has a meaning. So any cell in this matrix has a meaning. To give you an example, this value here, it means that this is the water, the quantity of water used to produce water. And the value that I put here, it means that it's the quantity of water to produce energy, and so on. So now, the value that I will put here, it means that this is the value of water to produce food. And here I have the end use of the water. And finally, here I have the total use of the water. So if you look to this row, all this row, it represents the balanced equation of water. And here you have the supply side, and here you have the demand side, and here the total side, the total quantities. And you can, if you make the summation by row, you will have a balanced equation that I showed you earlier. You can make the same thing for energy. The energy, the value that you put in this matrix at this position, it means this is the energy used to produce water. This is the energy used to produce energy. And this is the energy used to produce food. And finally, demand of energy and total use of energy, and so on. So as you can see that the matrix can represent all the interactions between water, energy, and food, okay, quantitatively. And also it has a balance. It's based on a balanced equation. This is another view, okay? This is the same matrix that before, but I put it in a more simple form. So in this here, you can see that this is the water for water, and here the water for energy, and water for food, and water at the end use, water at the total use, okay? Now, to write the equations, to start writing equations to represent this, what we showed you earlier. To write the equation, we will also use the same concept: water balance equation, energy balance equation, and food balance equation. In the water balance equation, the quantities that I showed you, it represents the quantities used from water to water, plus the quantities from water to energy, plus the quantities from water to food, plus the water at the demand side equal the total quantity. So the Y here, know the notation. Y, it means end use demand or demand side. X here represents the total quantities, and the Z, the Z represents the intersectoral use, which is you can imagine it's the supply side of the system. But if you look into this equation, it's not this equation. It's a matrix form because we have IG, we have different at the water sector. We have different technologies. We have different production technologies, and the energy sector also we have different production technologies, and the same thing for food. So the Z is actually it's a matrix that go from technology I of water towards a technology I of water, or from technology I of water towards a technology G in energy, and so on. So we put these balance equations for the three sectors. So if you look, for example, in the energy, you can see that in the representation, just to understand, E water, it means this is the quantities from energy towards water, from energy, the energy used in water, okay, and so on. Now, it's not the end. I need the equations. It doesn't tell me anything now. It can't be used in simulation. It can't represent a model. Now I want to transform these equations into model. It means that I want to make the relationship between the demand side and the supply side, okay? In a way that I can use it in simulation. It means that I want to increase my demand and see what are the effects. I change my technology and see what are the effects, and so on. So that's why we introduced what we call the technical coefficient. The technical coefficient is introduced in the intersectoral matrix, in the supply side matrix. How we define this technical coefficient? It's defined very simple. It's defined. It's in small a, defined as small a of water to energy, for example, I'm taking an example. It's the quantity of water used in energy production of this energy production technology divided by the total quantity produced by this energy technology. So as you can see, A has a particular definition. But from A, I can take Zij, which is the quantities that mentioned in the earlier equations, and here I can introduce A into my equations. This is an example to calculate A. I will not waste of time on this example. I will just give you the equations. Now the equations are changed, and I introduced A. And now, as you can see, that in the equation, the x, the total use is shown in the supply side, in the intersection function of A, or produced by A. Now, I'm changing the A. I'm introducing instead of A, Ij, I'm taking the matrix capital A. Now, A, it's a matrix, so this will simplify a little bit how to write the equation. Now, A, it's a matrix, X is the end use, total use, and so on. So these three equations, also represented in this form. This is the final matrix of equation. Okay, still we have, as you can see, here we have the technical coefficients, here we have the total use, and plus here we have the demand side, the end use, equal the total. Okay? I want this equation. Okay? To solve this equation, I will use the input-output theory, the Leontief inverse. It's very, very important, solution to this equation, this Leontief inverse. It gives you a very simple way. Actually, it's not as simple, but it's simple to calculate. It's very robust and interesting way to solve this type of equations. So in this type of equation, as you can see here, that you have X, the total use, is a function of the demand, it means the end use, and function of A, the technical coefficient, which represents what are in the A. In the A, we have the technology used to produce the different and allocation. So in A, we have technology and allocation, and Y is the final do. Now you have this equation. This equation could be used for simulation. How I can use? I can change Y, the demand. I want additional quantities. I can compute X, assuming that A is constant. I didn't change technology or allocation, but also I can simulate. I can change allocation and technology, and keeping Y constant and calculating X, and also X for each sector. And then also I can change both. I can change demand and I can change technology and allocation and calculating X. So actually, a final representation of the equation is this, because L here, it represents I minus A to the power minus 1. This is the Leontief inverse, the very famous Leontief inverse. Okay, so now, if I put it into the matrix representation, my matrix, it looks like this. And I will back direct and indirect effects. In the L matrix that I calculate, the Leontief inverse, in the Leontief inverse, the importance of this actually matrix is it has inside this matrix, you have the direct effects and the indirect effects. So the L generates all the impacts, direct plus indirect. So since they are embedded in this matrix, we can split these values, and you from L the direct effects, and we can extract the indirect effects. So now when we make simulation and we make the calculation, we know how much are the direct and how much are the indirect. And as I showed you in the first slide, so the indirect would be generated to infinity. So that's why in this equation, it can generate many, many times until this A become zero. So actually, it can generate many to the infinity these indirect effects, and this is very powerful of the L. Now, finally, talking about the modeling, I want just to introduce a very innovation that introduced in the QNexus model. We successfully split from the A, from the technical coefficient A, we split the technology, what we called an intensity related to each technology used in the Nexus, from the allocation. So now in the QNexus model, we have two additional variables, one related to the technology as an intensity of this technology, and the intensity of any production technology should be known, and also the allocation. The allocation is usually it's easy to find how much you are using from one sector, from one production to another sector. It's not very difficult to have this information. So those two variables are introduced in the QNexus. So we actually work on the equations to split these from the A, and then we successfully do that. You have the technology has his own variable, and which is the T for the intensity matrix and the allocation matrix. Now, this could building scenarios. I can, in my scenarios development, I can change the end use, I can change the technology, I can change the resource allocation. And each time I can actually, when I change these variables, compute the impacts from one sector to another on all sectors, not only water, not only energy, the three sectors together. The impacts are mutual in the three sectors together. Here I give you some examples of scenarios that we can use and how to translate these scenarios into variables, into changing variables in the model. And actually, just to conclude that why we are actually calculating these quantitative impacts from one sector to another. This is important in the decision making, because in the decision making, I have to give for the decision maker an economic effect of any scenario. Also, the decision maker should know the quantitative effect of any scenario. Here is the scenarios. So I can put here the economic, the quantitative, and the environmental effect, and so on. So I can put any other criteria, but the model here that we developed, it can inform about the quantitative effect. And this quantitative effect could be introduced into a more general decision-making process or multi-criteria decision-making matrix, and then we can actually calculate some sustainability index, whatever, and to inform about using this index to inform the policymaker about the different scenarios. Final word. I talked about three sectors, but it's in food. There's other sectors that could be ecosystems, economy, any other systems. So it can actually be applied not only for water and energy nexus or water and food nexus, it can also apply for to introduce other sectors into the equation. And this could be directly introduced, and I will show you in the QNexus web tool how this could be easily introduced and go beyond three sectors and go to 4, 5, 6, 7 Nexus sectors together using the same methodology, the same model, and the same accuracy in calculating these interactions. Okay, so now go to the QNexus model platform. And this platform actually, just one word before starting, this platform allows all the sectors to get together on the same platform and work together on the same project, on the same Nexus project, and to see each other, to share and to share scenarios and so on. So now, finish of part 1. Let's go to the part 2, sharing slides, and share my desktop to enter into the Nexus model web tool. Okay. I hope that you can see my screen. When you open QNexus website address, which is here, www.qnexus.net, you will have this page. Okay. Now, in here you have to log in. So you should have a username and password. If you don't have, you can create an account. So you can click on create an account, and here you can enter you can register in the Nexus in the tool, and then you will have the permission to access into the tool. My own email and password. I want to enter into my account. So once I enter into the system, assume that we are I'm a part of a Nexus project. It means that I represent the water sector, and I have 3 colleagues nationally that one represent the energy sector and another represent the food sector. The system will recognize this project by, once you enter into the system, it recognizes the 3 partners within this view. It means that when you log into the system using your username and password, and you are part of a project with other partners, all the 3 partners will be at the same environment in the tool. So they can visualize the data that are entered in this project, also communicate through different way, as I'll show you later on. So now let's say, for example, I'm the water sector. I have to start with the sectors. In here we have built already 3 sectors: water, energy, and food. But assuming that I want to add a new sector, so I can just add a sector, and I can name the sector and put the unit of this sector, and I can choose an icon and putting a new sector. So in this function, you can add the sectors that you want, the sector that you need. Once you finalize your sectors, you can go for each sector to start entering your processes or your technologies in each of these sectors. In the processes, you have to add a process. So you have to add your processes. And here I have already introduced 2, surface water and desalination. I can add another if I want. I just put the name, the description, and submit. This will show here. Later on, when I add my processes, I have to start entering the data for each process. I need to enter the total use, okay, for each process. And also, I need to enter the intensities. This is in the intensities, I can choose to add from water, for example, for water. Then I have to put my values, or water for energy. Also, I can put my values, and water for food. And finally, to finalize the input, I have to add the allocations. The allocation also from water to energy, for example. So the system will directly give me the opportunity to add the allocation based on what I entered earlier in the system as water and energy technologies. Okay. So I can do the same thing for energy and for food. So once this inputs is finalized, I can go for results. And results, of course, the example, the first thing that I have to build my reference scenario. This reference scenario is built on the actual technology used in the 3 sectors, the actual water quantities or resources quantities used in the Nexus system. So that's why it's referred as a reference scenario, or we can name it as business as usual scenario. So you can see the results for this reference scenario. You can show how much water is used and energy. I can show you just to save the time because we are late a little bit. So you can actually yourself try and see how these results could be seen. I have just to introduce to you, a very important thing is the scenario function. When you create a scenario in this tool, for example, I can show you, it will tell you, you want your scenario as a private or joint between all the partners. If you choose to private scenario, you can make scenario for yourself. But if you choose joint, all the other partners in your Nexus project, they can access this scenario and they can see what you are doing. What you change in the system, there's here an icon that, let's say a bell, that it shows for all the partners that there is modification on the project. And also the system can send emails for each of the partners that this change is made by any of the partners. So I will let you to go and explore more on the results. For example, you can see for the results, you can, let me take the reference. You can visualize the quantities from one sector. I can choose, for example, water towards all the sectors. And here I can choose to have direct values or the total values, direct plus indirect. So if I choose total, I can have this in a table form and also in a chart form. So I can view the results in a table or chart form. And finally, you can export your projects an Excel file to get all the inputs that you put. And we have features of the model that you can here put in satellite map. You can add your sectors, technologies used on the map, and it shows you whatever you enter the project, where is your resources, where is your technologies used in your project. And you have also the project description features. And here you can edit and add anything you want related to your scenarios and your project. Then everybody in your partners can see and comment on your project and simulation and scenarios. So as you can see, this platform can help all the actors to work together on the same project using a mathematical model in the background that give them the possibility to change the demand, to change technologies, and to visualize the effects in terms of quantities and charts, and also to differentiate between direct and indirect values. Okay, so this is, I will stop here because the time is running, and thank you for your presence again. And if you have any question, we have 10 minutes for questions.
Thank you, Dr. Karni. Thank you so much for this interesting and informative talk, and for the live demonstration on how to use the QNexus model platform. That was really very helpful. We would like now to open the floor for questions. We will start with the questions here in the chat box. We have two questions. The first one by Mr. Abdelrazak Boucharib. He's saying, in the MENA region, it is well known that the majority of water use comes from unconventional ways like desalination. In this case, how could we make a contribution in which we gather the three axes, water, food, with minimum energy and reuse? That's the first question.
I should answer directly the question, right?
Yes, yes. Yes,
yeah,
please.
It's better. Okay, thank you for the question. Yes, you are right that in MENA region we are mainly in the Gulf region. We are relying on desalination as a water resource. But this is actually, it's very important. This type of simulation is very important for also for this type of water production, because in desalination, we are using a huge amount of energy, let's say. Let's assume that we have a lot of energy used in desalination. So in this, when you make a little variation in your desalination, let's say, technology used, if you are using, let's say, this type of desalination plant in comparison with other desalination plants that consume less energy, and this type of variation, you can appreciate what are the impacts that could have on energy use and indirectly on water use, because energy is using water. And since water is very scarce in the region, so it's very important also to know these indirect effects that comes, because the decision is not only on the direct values. And here, yes, the indirect values are important. And using this model can inform about these indirect effects, and this would be very useful for decision making.
Thank you, Dr. Karnib. I'll move to the second question. By the way, Dr. Karnib, I had removed your video when you started talking, so if you wish to have it back, you can click on starting video again. Just wanted to let you know. So we have a question by Dr. Rula Bashour. We live in a country where data is scarce, and the Nexus platform is quite intensive in terms of data entry, which may be in many cases not available, especially at the level of policymakers. Are there, for example, default values for some processes? For example, kilowatt hour per meter cube of groundwater, etc.?
Thank you for the question. Yes, it's a very important question that you, and I'm glad that you mentioned the data availability problem or challenge. Of course, when you are dealing with a quantitative model, you need data. Otherwise, you cannot run or build up your model. But as I mentioned in the last slides on my presentation, that we introduce an intensity and allocation, two variables, to release the data availability to run the model using a standard data that could become from anywhere in the world. It's not needed. Once you decide your technology in any of the sectors, you can go and find the intensities of these technology around the world, where this technology is used, where the data is available. You can go and get this data. And you can make, let's say, adjustment to your context, to your particular context. And the intensities usually are available. By the way, the intensities from one sector to another is the inverse of the efficiency. And if you want to use another term of intensity, you can use, for example, the footprint. The footprint is also in the definition of intensity is the same definition. So actually, yes, the footprints are available somehow. So in this way, we are reducing a lot. That we needed is only the total use of each sector and the technology used, and based on that, we can figure out what are the intensity that should be introduced for each technology.
Before we move to the next question, Dr. Bashour is also asking whether there's an example or a base scenario for Lebanon.
Yes, I developed a base scenario, actually a preliminary base scenario, but this preliminary base scenario should be actually updated and put it, I mean, working more on this base scenario. And in the publications, you can see, in the QNexus publications, you can see a very small, let's say, base scenario on Lebanon, but it's just introduced to validate or to apply the model. We are now working on a more comprehensive scenario. Much more food products, crops, and mainly it will change towards the agriculture sector, because we have to introduce other crops and other technologies for irrigation that might change the results for the base scenario.
Thank you. Now we have a question by Dr. Rabia Muhtar. On achieving the outcomes of coherence among sectors, what are your thoughts on better engagement with stakeholders so we can achieve more sustainable resource management?
Thank you, Dr. Rabi, for your question. If I want to give a macro view, stakeholders could be introduced in the first stage of the evaluation of the Nexus system. The first stage, we are looking for qualitative challenges, and looking for scenarios, looking for solutions. Stakeholders could give their point of view, and you can take this point of view into consideration when we build our scenarios. Now the model is more quantitative, and in the model we have to run the model to find the impacts. We may go back again to stakeholders to give them the results of their thoughts or their scenarios, and give them what are these impacts in terms of quantities. And also we can get back to decision maker also. So yes, the interaction, not directly through one that are working on the system and go and back to inform stakeholders about the results and so on.
Thank you, Dr.
Unless yes, I can mention something, and this maybe it's for development in the web tool. I'm thinking, because this is, I thought that maybe we can introduce the stakeholders into the web tool. It means that once we build the three sectors, the partners in a project, we can let the stakeholders to be also access to the web tool, and they can only visualize results. They cannot change variables, so they can enter at any time into the tool and see what are the effects of each of these scenarios.
Thank you, Dr. Karnib. A few questions on the mathematical and the mathematical model and the data. The first one is, could we enter to the mathematical background of the QNexus model? And the second is by Mr. Muhammad Alami. How can I find reliable historical metadata of specific coordinates, latitude and longitude, to analyze suitability of energy installations for desalination for irrigation?
Actually, for the mathematical models, for mathematical equation, the web tool is based on the mathematical models of the QNexus, and it's built in the web tool. You cannot change it because you are not needed to change it anyway. But if you want to work on to make, for example, additional, let's say, progress on the mathematical side, you can take the published mathematical equations and work on it. So it's available. The second question related to very well the question, actually. The second question about the desalination, and could you repeat it?
Yeah. Yes. How can I find reliable historical metadata of specific coordinates, such as latitude and longitude, to analyze suitability of energy installations for desalination and irrigation?
Yes. Look, for desalination, maybe you can find it's not difficult to adjust to adjust the performance of the technology from one side to another. But in agriculture, yes, in agriculture it needs additional models to do that. And here I'm, for example, personally, I'm using AquaCrop software developed by FAO, the food organization, the International Food Organization, FAO. So I'm using this AquaCrop software. It's very interesting software that can let you actually introduce the climate data in your country and see what are the what are the water use needed for each type of crops. So it's very interesting, that could be used as as pre-calculation for the QNexus data.
Thank you, Dr. Karnib. One last question by Dr. Bashour. I have a question which is not really technical. After all these years of working with water, energy, food, and systems, do you think we will reach a point where at decision makers and policy level, we will start thinking in a WEF way and stop looking into silos, especially in Lebanon?
Actually, Dr. Bashour, as I said, we should because I showed to you that working in a silo is wrong. The data that you get from silo is wrong. So actually, if you are, for example, informing policymaking, you are misleading this policymaking because you are producing wrong values. You are not taking into account the indirect effects, the indirect impacts, and all the impacts actually. So we, as a specialist in this type of works, we have to say yes, stop using this silo concept, and the right way is to do it in a Nexus thinking, a Nexus concept approach to get actually the right values, the right impacts.
Thank you, Dr. Karnib. I'm just checking whether we have any more questions. I don't think so. Unless someone would like to type. I think that's it. Thank you so much again, Dr. Karnib.
Thank you for you, and thank you for the participants, all the participants. And
yes,
thanks for Prof. Rabi.
Thank you. Thank you. And I would like to thank everyone for joining us today and for contributing to the active discussion as well. Thank you so much. I appreciate. Okay. All right. I think we have come to an end. Thank you, everyone. Goodbye. Thank you very much, Dr. Karnib.
Bye.